And the next talk is by Professor Rahul Dandekar from IPHT, and he will be talking about hyperuniformity in 1D SOC model. Over to you, Professor Dandekar.
Okay, so I'll talk about hyperuniformity in the 1D Sandpile model. So let me start by first thanking the organizers for organizing this meeting. And it's great to hear all these talks. And I think it demonstrates how, like, what an amazing school of statistical physics that Deepak and Mustansir have created in India. And and as for my own experience at TIFR, uh, I owe a lot of my knowledge and attitude towards science to Deepak, and it's hard to find words to express my gratitude to him. So okay, so let me go ahead and talk about hyperuniformity. So what is hyperuniformity? So when you look at, let's say you're looking at a configuration from uh, the steady state of a given system. You don't know if whether it's non-equilibrium, equilibrium, whatever. You're given a certain configuration, and then you study it by looking at windows of size L, and then looking at number fluctuations within those windows. So you look at the number of particles, let's say, in a window of size L, and then you move this window all over the sample, and you look at how much the number of particles in this window fluctuates. Now, we know from our equilibrium statistical physics that if you're at a critical point, then the number of fluctuations diverges with as L increases. So the scale quantity diverges at a critical point, but if you're not at a critical point, but you're in an equilibrium system, then this quantity is finite. Uh, but there are some systems, especially non-equilibrium systems, where this quantity actually goes to zero as L increases. And those systems are said to exhibit hyperuniformity. So basically, on large scales, there are very low density fluctuations in these systems. So this property is called hyperuniformity, and this property is exhibited by quasi-crystals. This was like one of the first systems in which this was seen by Luck in 90s, Luck and Godrej, and then also it's seen in glasses in contact number fluctuations, in jammed systems, and what I'm going to focus on in this talk, in sandpile models. So sandpile models come in two varieties. One is driven dissipative. So most of you must know about sandpile models. I'll introduce it. I'll talk about sandpile models in more detail in the next slide. But sandpile models come in two varieties. One in which you have an open system and you're adding sand constantly, and that is called a driven dissipative model. And an example of hyperuniformity in that setting can be found in this paper by Grasberger, Dhar, and PK. In the Oslo model in 1D. So, and I'll talk about in the other setting where you have a closed system and you have a sandpile model on a closed system. So no sand is allowed to enter or exit the system. Okay, so hyperuniformity, as I said, is about suppression of density fluctuations. So sometimes it happens, especially in these sandpile models, it happens at a particular point, which is the critical point in these models. So there are two exponents that you can define. One is this divergence, or rather suppression of fluctuation. So basically, how does this quantity go to zero as L increases? That is governed by an exponent alpha. And as you approach the critical point, uh, how does the correlate? So basically, as you approach the critical point, you have growing hyperuniform regions. So at very high scales, you'll see normal fluctuations at very large length scales. But as you approach this hyperuniform point, these length scales will start increasing, and that is given by this exponent theta, which is the correlation length exponent. Okay, so let me talk about the sandpile model, which is the one I'll focus on in this talk. So the Abelian sandpile model was introduced by Bach, Tang, and Weisenfeld in the 90s. And it is a model of sand on a lattice, where this defines it on a 1D lattice. So Zi is the number of sand grains on a site. And what happens is, if there's a certain threshold, so if a site has more than 2 grains, so more than 1 grain in this way of speaking, then it topples, which means that the site is active, and then it gives 1 grain to each of its neighbors. So that is, if a site just has 1 grain, then nothing happens. But if it gets 1 more grain, then it topples. So that is the dynamics of the model. And it's usually studied, as I said, in a slowly driven system with open boundaries. So you can have a big lattice and you're adding sand throughout the lattice, and then it exits when it hits the boundaries. And this has a rich structure, and it shows self-organized criticality, which means that as you keep on adding sand, you naturally get diverging length scales, and uh, the avalanches which are created by adding one more sand grain, that is the dynamics which is created by adding one more sand grain, shows a power law exponents. And this state is the steady state is solvable, as was shown by Deepak in 1990. So in 1D, so in 2D, it has a rich structure. In 1D, this driven dissipative version doesn't really have a lot of structure to it. So I'll focus on the fixed energy version, which is the closed one, not the open one. So the 1D fixed energy SM, which means that you have a 1D lattice and it's a ring basically. So sand cannot enter or exit the system. Now you start with a certain density of sand. So now all configurations with no side greater with height greater than 1 are absorbing. So what absorbing means is that no dynamics happen. So if all sides have height less than 1, less than 2, then nothing will happen, and the system will stay like that forever. So if you start with any distribution of particles with total density less than 1, then eventually everything will topple and everything will relax until it finds an absorbing configuration. So how does one, but we suspect that as the density approaches 1, the system exhibits hyperuniformity on larger and larger length scales. So how does one study that? One needs a measure on the absorbing states. So one way to do that, which is inspired by the driven dissipative version, is to in the driven dissipative version, you add grains very slowly. So what happens is you add 1 grain and then you let the system relax, then you add 1 more grain and then you let the system relax, and so on. So similarly, one can drive this closed system ASM in a quasi-static way. What this means is that you have this rate alpha. So this is the slowly driven ASM. So if a site has 2 particles, then at rate 1, it gives one particle each to each of its neighbors. But let's say a site has height 1, then with a very small rate alpha, this particle can jump onto its neighbor, even though it is not above threshold. But what this does is that it creates a site above threshold, because this site will now have 2 grains, and now the sandpile relaxation can happen. So that is how you drive the dynamics. So this is a quasi-static driving if alpha is much less than 1. Sorry. So now considering this dynamics and taking alpha, the limit of alpha going to 0, what we find is that for all rho less than 1, there is a steady state on the absorbing configurations. And the measure on absorbing configurations is very simple. So basically, each absorbing configuration is a cluster of 1s, then some 0s, then some 1s, then some 0s, and so on. So one can write down a configuration in terms of its particle clusters. So let's say there's like K1 1s together, and then some 0s, and then K2 1s together, and then some 0s, and so on. So the weight of such a configuration in the steady state is basically just this. Now, This can be studied by looking at the grand canonical partition function, which is defined like this, which is basically the microcanonical, but multiplied by fugacities for both the number of for both the particles and the sites. And
2 more
because
minutes,
of
Rahul.
this, yeah,
2 more minutes, Rahul.
okay. So because of this measure, this becomes very simple. And now one can study this grand canonical partition function and find out the roots, of the denominator here, which give you the entropy of the steady state. And the first two roots, the ratio between them gives you the correlation length and so on. So here, the solution is given in terms of Lambert functions. And using properties of the Lambert functions, we find that the correlation length as rho approaches 1 diverges as 1 by 1 minus rho squared. Sorry. So these are the hyperuniformity exponents. And then, okay, so the conclusions are the quasi-static dynamics creates regularity over very long length scales. The average size of an avalanche. So basically, you see the question which physically arises is that there's this diverging length scale. It is much greater than the, what the trivial length scale in the system is, which is just the average distance between zeros. As you approach as rho approaches 1, the average distance between zeros is just 1 by 1 minus rho. But the system is correlated on much longer length scales. Why? So it seems to be related to the avalanches, because the avalanches create this very long range order. And if you look at the average size of an avalanche, for example, you can calculate that on that measure. And that also diverges with the same exponent as the correlation length. So it is, the avalanches seem to be creating the hyperuniformity. So there's a relation between the sandpile dynamics, which creates these very large avalanches, and the hyperuniformity that you find in these SOC systems. So the future directions are, understanding the relation between avalanches and hyperuniformity, and how robust it is to different methods of driving the system. Like I studied the quasi-static way of driving the system, but one could study a driven dissipative version, etc. So, okay, that's the end of my talk.
Thanks a lot, Rahul. Do we have any questions?
I think Satya has a question.
No, I don't have a question.
Your hand is raised.
Sorry.
And Mustansir Burma?
Yeah, okay. My question is simply the following. I mean, if your correlation length diverges and your time also diverges,
Yes.
what is, I mean, so you can surely associate a dynamical exponent Z. What is the value?
It's 2.
2.
Yeah.
Okay, thank you.
Yeah, no problem.
So I had a comment.
Yeah.
So if you have a system in which you add grains at random at all sites,
Yes.
then the number fluctuations will be proportional to volume. Variance of numbers fluctuations will be proportional to volume, and you won't get hyperuniformity.
Yes. No, but you're talking about the sandpile. So with sandpile relaxation.
Sandpile with driven dissipation.
Yes. But then in the steady state that you get in your the absorbing configurations that you have in your steady state will be hyperuniform, right?
I wouldn't think so, but I'm not sure.
Not in the 1D ASM, I guess, but
2D,
if you
2D.
study 2D ASM,
Even
for
in
example.
2D. Even in 2D.
Okay. Yeah, I'm not sure, but I suspect that there'll be hyperuniformity there.
Okay.
Yeah. Okay.
Hi Rahul, how is this related to the information hyperuniformity that was discovered by Chaikin et al.?
So it's not directly related, but yes, there is another way of studying these absorbing configurations, which is to look at the information of a certain information entropy of a configuration.
But
And
because the same sort of Sandpile models and the same configurations will show. So do you have the same exponents that they see? It's the same
no. So that depends on how you prepare the state and so on. So it depends on the measure of your on your absorbing states. So that measure changes on how you prepare the states. But there's certain universal behaviors of the information entropy. For example, it shows a cusp at the active absorbing transition and so on, which remain even in my treatment. So yeah, if you want more, you can look at the paper in EPL.
Okay, thanks.
Thank you.
Okay, thanks Rahul for the interesting talk.